All right, here we are again. It is again June 21st, 2016, and we are here for part 2 of our lecture in ENGR 2301, Engineering Statics. Okay, we have one more thing to get through today, and that is the method of sections. This is a method that well, if you want to solve for every single member, so if you want to solve for the force in every single member in a truss, I would say the method of joints is probably more effective. It's just a more systematic method. But if you wish to solve for the force in, say, a single member, just one member, or just two members, what is useful about it is that it allows you to directly jump. It allows you to leap beyond and directly solve for the force in that member. So. Trusses, method of sections. Trusses, method O sections. Method of sections. In order for an object to be in equilibrium, or as some people pronounce it, equilibrium. I mean, there might be somebody. In order for an object to be in equilibrium, every section or piece of that object must be in equilibrium. So if I were to take a rather grim example, if someone were standing at the front of the classroom, I could draw a free body diagram of them as a whole object. I could draw a free body diagram of a person, and I am god awful at drawing human beings. I mostly draw with a straight edge. It kind of looks like a turtle. A person. And I could draw a global free body diagram. And if I did that, I would have the weight coming down from the center of mass, and I would have a pair of normal forces representing their feet, right? And that is how, that is the condition for the global free body diagram. However, if I want a rather grim example, I could cut this person into tiny pieces. So I could draw a free body diagram of just their head. And what would the forces on there be? Well, I would have the weight of just their head and the normal force representing the contact force and the bonds between their neck and their head. Or, if I wanted to, I could draw a free body diagram of just their arm, or just a piece of their arm. Their arm is a rectangle. And they would have the weight vector for their arm would pass through the center of mass of their arm, and then there would be a corresponding material force, or not really normal force, more like a tension or something like that. You could get really detailed, even break it down muscle by muscle and things like that. And you could draw a free body diagram of just their arm. And we could go deeper and deeper. We could do it finger by finger. We could do it capillary by capillary. It doesn't matter how small I divide this person's body up. I could still draw a free body diagram of this person. I promise I'm not a serial killer. The same is true for trusses. Oh, wow, we need more. Theory slides. Huh? No, I haven't been watching Dexter. Okay, so although I have watched, well, I watched all of Dexter except for the last season. I made it partway through the last season. And I was just like, meh. Huh? Yeah, pretty much. Yeah. The last season just kind of peters out. It's just like, like The Matrix. That was a great movie, and it's a shame they never made those sequels they were planning on. It had such potential. They just never got funding for it. It's a shame they never made those. Just like those Star Wars prequels. I wish they'd made them, but it just never happened. And also the Highlander movies. Well, everything except the first one, obviously. All the Highlander sequels. That just never happened. Huh? Burn the heretic. Someone said one of the later Highlander movies is okay, and I was like, burn the heretic. I don't want to. Okay. Okay, method of sections. Let's get through this. I'll describe it briefly in theory, but this is one of those things that's best described by illustration, by example. Method of sections. So, probably one, get reactions. Two, cut out a section that is convenient. What do I mean by convenient? A, make sure the section includes a cut on the member you wish to solve, on the member you want the force for, the internal force for. I will say the newest Star Wars movie is actually pretty good. I like it. Although, have y'all, huh? Ooh, huh? Essentially, yes. Although, have y'all seen it? Uh, it was not horrible. Oh. Ugh. Although, the one thing I wish they'd done, like, in that scene where like the big laser is coming down and destroying the planet with all the people standing around on it, I just wish that in the background they had put like Jar Jar just somewhere in the background. That would have been so easy. Just a common little Easter egg, just like he, just in the background somewhere. Just make him on the planet that was blown up. Huh? Yeah, him and George Lucas just embracing. Yeah, that'd be great. Okay. I'm sorry. Huh? I heard that theory. That's hilarious. Anyway, yes, there's a fan theory that someone on Reddit spelled out way to way too much depth that Jar Jar is actually a secret Sith Dark Lord planning the whole series. Huh? Yeah. Okay. And his actual like bumbling antics were actually an example of some kung fu technique called like the drunken master kung fu technique or something. Anyway, that has absolutely nothing to do with statics, but that's okay. So yeah, make sure the section includes a cut on the member you want the force for. Um, Make sure that the cut does not include more than 3 unknowns. More than 3 unknowns, because that's all we'll be able to solve for. 3. Um, let's see. Apply equations of equilibrium of equilibrium, treating the section as a single rigid body. And then finally, a note. This is important. All cuts must be transverse to a member. In other words, your cut line has to go across a member. You don't want to try to run a cut line along a member. That's going to cause you problems. It's going to be weird. Okay. So there's method of sections. You got it. The rest is just math, right? That's it. No? But it's simple. I just described the whole thing. Oh, yeah. The cross-sectional method of joints? You'll see the difference. Okay. So, look at this here. 6.44 in the Beer Vector Mechanics book. Determine the force in member FG and FH in member of the truss shown. So we want FG and FH. Imagine what it would take to solve this using method of joints. There are no zero force members here. FG and FH. FG and FH. FG and FH. Okay, yeah, there are no zero force members here. So we could do method of joints. We'd have to get the reactions on both sides and then slowly work our way across. Like we'd have to start here. Or for example, we could start here. There's different ways to do it, but we could start here and get this one and this one. And then we could go to this joint, get this one, then go to this joint, then go to this joint, then go to this. It's gonna take a lot of work. We're gonna be here an hour trying to solve that one, right? But what if I did the following? What if I said, you know what, I really don't care about the entire truss. This problem is only asking about members FG and FH, so nothing else in the universe matters. So, you know what, I don't use purple enough. I'm going to use purple. I'm going to say, hey, what if I look at only this piece? What if I look at only this piece? I'm going to consider only this piece. I could just as well consider this piece over here. The only reason I chose this was because I had a pin that could complicate things, even though it won't. But there's 2 bays over here, 3 bays over here. That's going to make it a little simpler to do it over here, although not by much. Okay. So I'm going to need, I don't care what this reaction is. I do not care.
How'd you know to cut it in half like that? Not just draw the individual triangle from FG to FH.
FG to FH. Well, I could just cut out the entire piece, but notice that'll give me a whole bunch of unknowns. I would have I could like cut this portion out here, but then that would give me 1, 2, 3, 4, 5, 6. Every time my cut line crosses a member, that's an unknown. Every time my cut line crosses a member, this is an unknown. And see, what I have here is I have a cut. And so now, the devil of this is just creating the cut. There's a certain amount of experience that goes into just figuring out where to cut this thing. So that's something that you gain through practice. I can look at this and say, oh, this is probably a good cut location. And sometimes the cut you'll want to take will be a little bit different. Like you might have a cut that goes, if I just wanted this piece, I might do, if I only wanted FH, I might do a cut like this. And then that turn would allow me to avoid that load there. But anyway, you'll see. So the first thing I'm going to do is solve for necessary reactions. In this case, that's going to be JY. Using a global free body diagram. So ignore the cut right now and look at the global system. Look at everything here. I'm going to have BY and JY. That's a get. That's meant to be a G, not a B. Still not clear? G. It's one of those like block G's. It's one of those block letters you have in like an illuminated manuscript or something. There you go. Get necessary reactions using global free body diagram. So I'm just going to say, you know what? Sum of moments about point B equals, so each of these is 2.4 meters. Well, this is going to be clockwise, clockwise, counterclockwise, negative, negative, positive. Negative 12 kilonewtons times a distance of 4.8 meters minus 12 kilonewtons times a distance of, that looks like 6.2 meters, right? Yeah, 6.2. And then plus JY times a distance of 9.6 meters. JY is right here. And it's directly under the beam, or under the column here. If it looks like it's separate, your eyes are clearly deceiving you. It's clearly right under the column there. And all of this equals 0. Why? Did I flub that up? Derp. Yeah, it's 7.2. Math is hard. 7.2. Okay. And why does it all equal 0? Because it's an equilibrium and this is statics class. Okay. So finally, JY is equal to 12 times 4.8 plus 12 times 7.2 all over, oh, that's not right. 7.2, not 7.8. 7.2 all over 9.6. And this will come to 12 times 4.8 plus 12 times 7.2 all over 9.6, which comes to exactly 15 kilonewtons. Now, here's where the magic happens. Okay, so 2, draw a free body diagram of section. So what I'm going to do is I am going to draw everything, I'm just going to draw the section as a block. This is G, G, I, H, and J. And the forces I have on here are 15 kilonewtons here, 12 kilonewtons here. Notice you do need to consider all external forces on this. 12 kilonewtons. Also sometimes referred to as a kilonewton. by some folks. I don't know, maybe. This will be FEG. FEG here. Basically, every member that is cut, I'm replacing with a force. This one will be FG. And this one is FH. Huh? Oh, okay. This one is FFH. Oh, and the force triangle here, let's see. That looks like a 3, 4, 5, doesn't it? Yeah, that's a 3, 4, 5. Huh? FGH? FGH, I do not need to include that because that's an internal force in the cut. I'm only concerned with the external forces on the cut. And when I cut it, each of the member forces that we cut becomes an external force. So this is then a 4, 3, 5 triangle. Coming from the word Greek word tri meaning 3 and angle meaning angle. Okay, so I am going to let's see, and my dimensions here I'm going to have 2.4 and 1.8. Let me just label those really quickly for convenience. This dimension here is 2.4. And 1.8 meters.
I thought that's how you got the 3, 4, 5 triangle, right?
Yes. But that's 1.8. The question was, that's how I got the 3, 4, 5. Yes, but however, this is referring to this bay here. However, it turns out that all these bays are of the same width, so that works. Oh, and for nomenclature, vocab, each of these rectangles in a truss or structure is referred to as a bay.
Bay?
Huh?
So bay?
So bay?
It's bay?
It's bay?
Oh, okay.
A bay, B-A-Y.
A-Y.
What do you think I said? Okay. B-A-Y. Bay. I need a drink. Okay. Huh? Well, been a long day, yes. Okay, so what I'm going to do is I am going to do a sum of moments about G. Because look at this. Look what's going to happen when I do that. Something magical happens when I do that. This force, and this force all have lines of action that go through point G. So my life becomes a lot simpler. So I'm just going to say, hey, look, FH is going to have a negative about G, negative moment, negative FH. Oh, and then I should probably put like step 3, solve for unknowns, for forces. Yes. Oh, yeah, thank you. FH. What's a letter among friends? Times 4 over 5 to get the x component of it, times a perpendicular distance of 1.8 meters. That's the moment generated by this. And then a positive moment plus 15 kilonewtons times a distance of 2.4 meters. Like so. And then equals 0 because this is statics class. The 4 over 5 again is to give us the x component of the, oh wait, I'm an idiot. I'm sorry. Derp. It helps if I get it right the first time. Negative FFH times 1.8 meters. Much simpler. Chaos, confusion, disorder, my work is done here. So FFH then is going to be 15 times 2.4 over 1.8, which I just happen to know is 15 times 4 over 3. 15 over 3 is 5, so this is going to be 20 kilonewtons in tension. And that's our answer for FFH. So we have that one. And then finally, I will simply say the sum of forces in the vertical direction.
So,
yes.
FEG and FFG don't do anything to... Oh, because it's at the point G.
Exactly.
Sorry.
Sum of Fy, the question was, these two don't generate any moment about G? Yes, that's correct. Sum of forces in the vertical direction, I'm going to have 15 kilonewtons minus 12 kilonewtons. That looks bad. Minus 12 kilonewtons minus Fg times 3 over 5 for the vertical component equals 0. So this is then 3, positive 3, negative 3, positive 3. So FFG equals 3 kilonewtons times 5 over 3, or just 5 kilonewtons. Also tension. And that's the other answer. I think. Let me double check that. That would be negative 3, and yes, 5 kilonewtons tension. And that's it, yes.
Will you ever need more than one section for one problem?
Huh? Oh, sometimes, yeah, so you may actually need more than one section in one problem. For example, especially, the question was, do you ever need more than one section in one problem? Yes, sometimes you do. For example, what if I had asked you to find the force in FFH and the force in FCD? Well, there's not going to be any convenient cut that you can make that will include both of those. That's just not going to happen. I don't think there's any way that you can cut this that will have both this one and this one while only cutting one other member, because that is what would allow you to have only 3 unknowns. Questions on that? So you'd have to work with multiple cuts. Other questions? Okay. Let's see. Determine the forces in member DF. So we want this one. And CD in the truss shown. I'm looking at this and trying to create a clever cut. And you know what? I think I'm going to do some witchcraft again and perhaps solve this without finding the reactions. Well, actually, which would you rather have me do? Would you rather have me solve for it with reactions or without reactions? You'd prefer the reactions? Okay, fine. If I cut it without reactions, we'd end up with a bigger cut. I'd use this cut right here. But with reactions, I'm going to have this cut right here. Okay. All right. Let's get the reactions on this thing. So I'm going to have a AX here and a BX here. Ooh, this is a fun one. and a y here. This is one of the rare ones that I actually need to find all three reactions. Isn't that lovely? Okay. So, you know what? For the purpose of finding reactions, I am going to say that all of these are equivalent to, we can only do this for the purpose of finding reactions. That's it, not for finding internal member forces. But for the purposes of finding reactions, all of this is equivalent to a 40 kilonewton force, 4.5 meters, or actually 1.5 meters from that edge right there. .5 meters here, and with this being 40 kilonewtons. Again, for the purpose of finding reactions and reactions alone, you can replace all the loads on the structure with an equivalent load, with the same total load acting about the centroid of those loads. You can see that the center of all of these loads is halfway between E and G, right? And the total load is going to be 40 kilonewtons. So for my calculation purposes, I am just going to say, you know what, I'm just going to treat them as one load. That will make my calculations a lot simpler. Okay, first of all, I'm going to say sum of forces in the y direction are equal to AY plus 40 kilonewtons, or actually minus 40 kilonewtons, AY minus 40 kilonewtons equals 0. Therefore, AY is equal to positive 40 kilonewtons. So we have that one. Sum of moments about A. I am going to get BX, that's going to be a positive moment, times a distance of 5 meters, then minus 40 kilonewtons, times the distance, this is 1.5, 3 and 3, so a total of 7.5. 7.5 meters equals 0. So BX equals 40 times 7.5 over 5. This is basically 1.5, right? So this should be 60 kilonewtons. Is BX. By a sum of forces in the x direction, I'm going to have questions? Okay. AX, I'm going to have AX plus BX equals 0. AX equals negative BX equals negative 60 kilonewtons, or 60 kilonewtons to the left. Well, this one is 60 kilonewtons to the right. So AX is actually going to be going to the left. We can kind of think of this in terms of couples. If we want to analyze this in terms of how the structure is behaving, all of the vertical load is taken by this support here. But then in terms of the moment, we need to resist the moment. So I have a couple here that is acting counterclockwise, and these forces are producing a clockwise rotation, and these are balancing out. So now I will simply, well, sort of simply, make a cut on this truss. And so I need to include this one, and I want to include only one other if possible. And it looks like I can do that just fine, like so. This piece here. So all this other stuff to the right is going to fall away, and I'm only going to be concerned with this piece here. And again, I'm going to draw it as a block, or in this case, a triangle. Again, we decide our cuts on the question was, how do we decide our cuts? We want our cut to include two things. One, any force that we're looking for, and 2, the minimum number of other members possible. So I could cut, say, like, if I tried to cut like this way with this thing here, I would get 2 additional unknowns, and that wouldn't work, because then I'll have 4 unknowns, and I'll have trouble solving for that. But by solving simply here, by taking this one here, I have only 3 unknowns, so that's something I can work with. So I'm going to draw the external forces and the unknown forces on here. Bx, I'm going to have 60 kilonewtons here. Let me label the points here. I'm going to have B, D, D, and A. I have the 60 kilonewtons here. No. For the B, it's going to the right. I have 60 kilonewtons here. And I have 40 kilonewtons here. Then I have FAC, FAC, FCD, and then I have this force here, FBF. I want the force triangle on that thing. FBF. With a force triangle of, let's see, what's that going to be? Huh? Oh, thank you, DF. Yes, yes, yes. FDF, this one here. And the force triangle is going to be 12 by 5, and what is that? Yeah, sounds about right. Yeah, 13. So it's one of our special triangles. Like so. Now, let's see. Let me label a few dimensions on here. I think that'll help. Namely, I have this horizontal dimension here, 3. But this dimension here, I'm going to need for moments, I think. This one here, the vertical dimension, has to be 5/4, or 1.25 meters. How did I get that? Well, each of these bays is, well, I don't know if the word bay can properly be applied to a triangular section, but whatever, I'll call them bays anyway. Each of these is from A to C, C to E, etc., is 3 meters. So the total horizontal distance is 12 meters. So each of these represents 1/4 of the total horizontal, which means since this is the same triangle, each step here must be 1/4 of the vertical. 5/4, 1.25 meters. Good? Okay. So this is, I'll put it here as well. 1.25 meters, 1.25 meters, and 3 meters. And if we need it, this to here is then 3.75 meters. Okay, so, and this here is point C. C. Okay, I think what I'm going to do is I am going to, some moments, if I can, you know what, I'm going to try to, I want to jump to something that's going to give me just one unknown. So I'm going to pick, say, moments about D. You know, I could do some moments about C. That would also, because both these points also pass through point C. But then I'm going to have to break force D into two different pieces for moments, and I'm lazy. So I'm just going to do some moments about D instead. And just not worry about it. So some moments about D. Let's see. FAC is going to generate a negative moment times a perpendicular distance of 3.75 meters. Then, so neither FCD nor FDF will generate a moment about D because their lines of action go through point D. Then, minus 40 kilonewtons times 3 meters plus 60 kilonewtons times 3.75 meters. And then plus 60 kilonewtons, again positive and positive, times 1.25 meters. And all of this equals 0 because this is statics class. So negative 3.75 FAC. You know what? I'm just going to throw all this in my calculator, all this mess in my calculator. So negative 40 times 3 plus 60 times 3.75 plus 60 times 1.25 comes to plus 180 kilonewtons equals 0. And from this, I can easily conclude that FAC is equal to 180 over 3.75, 48 kilonewtons. And that's not one of our answers, but that's okay. We can use this now for other purposes. So now I'm simply going, so now that I have this, I can say sum of forces in the x direction equals FAC plus FDF times 12 over 13. And then, hey, plus 60 minus 60, 0. Those go away. Plus 60 minus 60, poof, they're gone. So this leads us inexorably to that FDF equals negative 48 times 13 over 12, which this is 4, 13 times 4 is, let's see, 40 and 52, right? Negative 52 kilonewtons, like so. Compression. So that's FDF. And then finally, sum of forces in the y direction. I'm going to have 40 kilonewtons, this one here, plus FCD, plus FDF times 5 over 13, equals 0. However, FCD then will be negative 40 minus negative 52 times 5 over 13, and I'm feeling exceptionally lazy. I could do that in my head, but I'm gonna, well, actually, no, I can do this. Let me see. So this is negative 4, right? 52 divided by 13 is 4. So then negative 4 times 5 is 20, so negative 20 plus 20, so negative 20, right? Negative 20 kilonewtons compression equals FCD. And there you have it. The method of sections. So again, the method of sections, the power of the method of sections is that it allows us to directly leap beyond where we would otherwise be. The method of joints, if I wanted to do this using the method of joints, I have no zero force members here. So if I want this one, I'm going to first have to draw a free body diagram of this joint. I could draw this one, but that's not going to help me at all because I have way too many unknowns. So then I could draw a free body diagram of this one to get this one and this one. That's still going to have a lot of problems because if I draw this one, oh my god, I'm probably going to have to start from this end, get this one and this one, then maybe do this one, this one, this one, this one, this one, and this one. I'm going to have to draw 6 to 8 free body diagrams to solve for those two stinking forces using the method of joints. But if I use the method of sections, I can draw a single diagram and leap directly to the solution for those forces. Okay, questions on this nonsense?
Why do we divide it by 4?
Wait, what, huh?
Why do we divide the dimensions of the big triangle by 4?
Oh, in order to get the, why did we divide by 4 to get the 1.25? Again, each of these bays is 1/4 of the total, right? And so that means from B to D, it must go up by a total of 5/4. 1/4 of the total height. It's a similar triangles thing. All right, let's see. There is another example I could work through, but I think I'll leave it at that. Don't know if we have quite enough time for that one. Let's see. So you have your homework to work on. I think I need to throw some solutions on the website still. Let's see. Tomorrow we are now done with trusses. Tomorrow we'll look over some homework, look at a little bit more on frames, simple frames and machines, and then that'll do it. So, and then on Thursday we will actually be getting into shear and bending moment diagrams, if you can believe it already. So that should do it. You have everything you need. If you have any questions and need to see me, I'll be in my office from here until a little bit before 4 or so, depending on how lazy I'm feeling. That should do it. Feel free to come up and ask any questions if you need something brief. Good class. I'll see you tomorrow. And as always, thank you.